Rotational work and energy. If you recall, for translational motion, the work done on an object by a force is equal to the force times the displacement of the object. If the force and the displacement are in the same direction, work is positive. If they are in opposite directions, work has a negative value. If we apply a force to this wheel, it moves a distance s, which is the magnitude of its displacement. Doing so, the wheel rotates through an angle, theta, which is equal to s over r, where s is equal to the arc length of the wheel at a radius r. Solving this for s, we get r times theta. And plugging this into our work expression, we see that the work done by our force is equal to F times R times theta. The torque on the wheel from our force is equal to F times R, because R is the value for our lever arm. Plugging this back into our work expression, we get an expression for work that involves rotational variables if theta is in radians. We can call this rotational work. The rotational kinetic energy of a rigid body rotating about a fixed axis with angular speed omega and moment of inertia I is equal to 1/2 I omega squared. For this, omega is in radians per second. Does this look kind of familiar? We previously saw that translational kinetic energy is equal to 1/2 mv squared. This equation fits the pattern, since moment of inertia is the rotational analog to mass, and angular speed is the rotational analog to linear speed. Remember, total mechanical energy is the sum of all kinetic and potential energies. This means that we can now include our rotational kinetic energy term in our expression for total mechanical energy. Total mechanical energy equals translational kinetic energy plus rotational kinetic energy plus gravitational potential energy. And expanding it looks like this. Also remember that total mechanical energy is conserved if the net work done by non-conservative external forces equals 0. That is, that the final total mechanical energy will be equal to the total initial mechanical energy. Now, non-conservative work includes not only the work done by non-conservative external forces, but also the work done by non-conservative external torques. Let's look at an example problem. A cylinder rolls down a hill from a height of 10 meters. The cylinder has a mass of 20 kilograms and a radius of 0.75 meters. The speed of the cylinder at the bottom of the hill is 12 meters per second. What is its angular speed at the bottom of the hill? Ignore friction and air resistance. Okay, what are we given? The height that the cylinder starts at is 10 meters above the bottom of the hill. The mass of the cylinder is 20 kilograms, and its radius is 0.75 meters. The cylinder's speed at the bottom of the hill is 12 meters per second. That's the final speed, V final. And what are we looking for? The angular speed at the bottom of the hill, omega final. Now we need an equation. We're told to ignore friction and air resistance, which would be the non-conservative forces we would have to worry about. So we can say that the work done by non-conservative forces and torques is equal to 0. And total final mechanical energy should equal total initial mechanical energy. Remember, this is our equation for total mechanical energy. So we'll set the final total mechanical energy equal to the final initial mechanical energy. And now we substitute the expression for each of these terms. Now we can get rid of a few of these terms. H final is at the bottom of the hill, so it has a value of 0. That means this whole term equals 0. The cylinder's initial speed at the top of the hill, V initial, is equal to 0, so this term equals 0. And the cylinder's initial angular speed, omega initial, is equal to 0, so this term also goes away. Now, since we're looking for omega final, we'll solve this equation for omega final. We know what m, g, h initial, and v final are, but what is I equal to? We need to look at our table to find the expression for the moment of inertia of a solid cylinder. I equals 1/2 mr squared. So we'll plug that in for our I terms. Now we can plug in all of our given values. And finally, we can use our calculator to solve, getting a value of 14 radians per second for the angular speed of the cylinder at the bottom of the hill.